So what is the Cern LHC? A little background history on Cern. It is a research company built in the 1950s in France and Switzerland with the sole purpose of solving what the universe is made of through the use of engineering and scientific reasoning. So the first question is, what is the building blocks of our universe? What are the building blocks of the building blocks? So we know that an atom is made of protons, neutrons, and electrons. Protons being positively charged, electrons being negatively charged. But what makes up a proton? Well, imagine this. Imagine a kid has two toy cars. And you can imagine a baby, he's playful, smashes these two cars together, and what do you get? You can see the axles, you can see the wheels, you can see what makes up this car. And as you can see in the picture here, the kid's smashing two red cars together, and bam, there are the parts. So scientists were wondering how they could find what a proton was made of, and they had no idea how to do so. Well, they imagined if you take these atoms, specifically protons, speed them up at high velocity near the speed of light, and smash them together. And what you get is an explosion and the parts of these atoms, and it's supposed to be a representation of what happens shortly after the Big Bang. So the first type of particle collider that they used, particle collider being the machine they used to do this, was a linear format. And it shot these hydrogen atoms that had their electron strips, so essentially they're just a proton. And they were shot down a copper tube. And these protons, they were sent in packets, were sped up, and this, as you can see, the copper tube and the protons, and they were used, because they were positive, you could use negatively charged magnets to send these protons down this tube. These protons would be sped up near the speed of light and sent around the circular tube near the very end, where they would be separated into protons that went clockwise and protons that went counterclockwise. As you can see, the packets are going counterclockwise, and then there would be an occurrence point somewhere along this circular tube where the collision would occur, and monitors with receptors would record this. Well, these receptors would come back to this computer database, which would calculate in various different ways, too complicated for the human mind to understand, to make a visual representation of what this collision looked like. And most of these collisions were the exact same and had no significance whatsoever. But after you do this over and over and over again, eventually you'll get an occurrence that would take way too long to be manually done that is different than the rest, where you can see a particle that wasn't there before. And the computer database will highlight this one and allow it to be compared to what would be an ideal collision, something that normally happens. And then scientists will take these two pictures, look for what's different, and try and solve for what it is. So how do they solve for what these new ones are? Well, we'll talk about that later. Next way they did this was the circular representation. Like the linear one, it used a copper tube, but instead it had several series of circular tubes. And this is the same format that's used in the LHC. So let's talk about the Cern LHC specifically. It's built underground beneath the borders of France and Switzerland. And this is the big highlight of CERN, their company, is their particle collider. So there's the initial tube, and this is where the hydrogens are stripped of their electrons and sent down the straight tube and accelerated to 91.6% the speed of light. And likewise in the linear version, they're sent in packets. And down this initial tube, they're split up into 4 separate tubes. Again, as I said, they're sped up to 91.6% of the speed of light. And once they reach the speed, they go to the proton synchrotron, also known as the PS. In this tube, they are again sped up to 99.9% the speed of light. So once these 4 packets, they sped up to this 91.6% of the speed of light, they are regrouped together back at the PS. And here's a visual representation of the initial tube, as you can see, and then the PS. And that's 91.6% the speed of light and 99. But what is that second tube up there? Well, that's called the super proton synchrotron, also known as the SPS. Inside this tube, these protons are sped up to 450 giga-electrovolts. You may be wondering what that is. It's a way to measure electron speed, and it's extremely fast, unbelievably fast. It's mind-boggling. It's so fast that instead of speeding up more, these protons began to gain weight and mass, like they're eating hamburgers. They began to expand. And in this final stage, these packets, just like in the linear, are sent clockwise and counterclockwise, and they are where these collisions occur. And now there's 4 major detectors and they all have their own separate significance in what they do. And they're lined up along this final tube. The 4 are called the ALICE, ATLAS, CMS, and LHCb. So ALICE answers 3 questions. It answers what happens when matter is heated up 100,000 times the heat of the sun. The second question, it asks why are the protons and neutrons weigh 100 times more than the quarks they're made of? And question 3 is, can quarks be freed from protons and neutrons? ATLAS and CMS have the same functions. They look for particles that are almost, we know they're theoretical, they're hidden particles like the Higgs boson or dark matter. We know they're there, we know that they're necessary for physics to work, but we can't find them. But the only difference between CMS is it was built above ground and then later placed into the Cern Lhc. And then the LHCb. You may be wondering, oh, LHC, that's Large Hadron Collider, but B stands for beauty. And that is the quark it is known for solving for. It also solves for gluons, which hold quarks together. It solves for what gluons are, how they operate, and it also solves for where did all the antimatter go. If you don't already know, our universe is made of matter and antimatter. When they collide, they explode in a mass explosion and completely obliterate each other. But why is matter left over? Where did all the antimatter go? And that's what the LHCb solves for. Thank you for watching. If you have any questions, leave a comment in the box below. Thank you very much.